Okay. Right, we ready? The camera is rolling. NPN transistors. Okay. So, transistor, semiconductor device made out of silicon. It's used to amplify or switch electronic signals. Okay? Depending on how the circuit's made, they're used for lots of different things. A transistor is basically made of semiconductor material, but it has three terminals. So we have the base, we have the collector, and we have the emitter. So normally when you get a transistor out of the pack, you need to establish which one's which before you can use it, and we do that by looking at the pinout. Okay, so a voltage or a current applied to one pair of the transistor's terminals changes the current flowing through another pair of terminals. So effectively, what that means is if we have current flowing into the base, a little bit of current flowing into the base, then we will get a much larger current flowing between the collector and the emitter. The current that goes into the base does come out of the emitter as well, so that's why we call it B and E junction. If you think of it like a remote controlled switch, you can control the current going down here by changing the current here. Okay? So it has a gain. Gain. Does anyone know what the gain of a transistor is? Or what we call it? HFE is the correct answer. So, first of all though, just simple example, if we get a transistor like this, exactly like that circuit there, if we connected the base to 0 volts, no current would be flowing into the base. So what would the state of the lamp be? It would be off, wouldn't it? Because we've got no current flowing in here. So effectively the resistance of the transistor would become infinitely high and nothing would flow through from the lamp. But if we connect the input lead to the base to the power supply, then current can flow into the base. That then opens up the NPN junction inside, and the resistance of the transistor goes right down. Okay, it go down to nearly zero. So you go from, it's basically like a very sort of clever variable resistor. So therefore, if you've got current flowing into there, then a much larger current can flow through there. And the ratio of the currents is given by this HFE, which is equal to the current going through the collector divided by the current going through the base.
Interrupting this YouTube video.
I've ruined my YouTube channel though.
We'll edit it out.
I'm going to retire.
Be in the edit.
Transistors by Joe. Right. Yeah, it just photobombed it. Okay, so we've got IC coming down here, the collector current, we've got IB going through there. So what we can do, we can have a circuit like this where we change the voltage flowing into the base. Notice, we always have a resistor there. What do you think that might be for? Jordan! What do we generally use resistors for?
Protection.
Yeah, in some respects it is, okay? The resistance of the current flowing into the base of the transistor is low, which means if you don't put a resistor there, it will suck current out, down through there. It'll affect your potential divider if you've got one of those. It'll load that too much, but also you can end up overheating the transistor. Okay, so we always have a resistor connected to the base. Here we've got a potentiometer to vary the voltage. So as we're going to increase the voltage here, the current's going to start flowing into the base. That's going to open the taps. It's like a big sort of tap, and the current's going to start flowing through the collector into the transistor and out of the emitter there. Now if you think about it, when we went back to thyristors, when the thyristor was on fully, what was the voltage across it? Can you remember? When it was on, what would the voltage here be?
Is it half?
Nope. So when the transistor is fully on, that's just like a wire. Its resistance is low.
Or is it thick?
So it's going to be, no, because you've got the resistor here. So if you were to, it always causes a problem. If that's 6 volts and you measure the voltage here, what do you get?
Oh right, yeah, it's connected to naught, so it's just nothing.
Exactly.
Yeah.
So don't get your ear. You're thinking too hard. We're not thinking hard enough. I don't know. Either way, but don't get that mixed up. So, okay. So when the transistor is fully on, actually the voltage across it will be 0. When the transistor is fully off, then the voltage across it will be 6 volts.
Yeah.
Okay. So what's going to happen is, if we start building up the voltage slowly going into there, then it'll start off with a high voltage here, and it'll drop. And eventually, if it drops to half the supply voltage, then half of the voltage is across the resistor, and half the voltage is across the transistor. And it'll be like this is when it's in its half on, half off state. Wrong thing. Okay? So that means we can draw what's called a voltage characteristics graph, where I prepared earlier here, where we can actually look at if we're raising the input voltage, when we can look at the voltage across the transistor, we end up with 3 obvious areas of the graph. The first part is called the cutoff area. There's no current flowing through the transistor. It's completely off. All the voltage is across the transistor. None of it is across the load, the bulb or the resistor, wherever it is. So it's completely off. We call that cutoff. And there's our little friend, 0.7 volts. Yeah? How many times does he pop up? We get to the end of this course and you just know that 0.7 volts is your favourite voltage in the world. We know at 0.7 volts, that little junction, the semiconductor starts to break and open up, and holes flow one way, electrons flow another, and we start to conduct. So here's where the bulb would start lighting up, some current is starting to flow, and the voltage across the transistor is dropping. This region here is called the linear region, and it's the part of the transistor where base current going in is going to be proportional to the collector current. Because remember, we've got IC, the collector current, equals the base current multiplied by HFE. That's only actually true within this region. Because once you've got the transistor saturated, you know, like at home when you turn on a tap, at first, as you turn it, the flow gets stronger, doesn't it? But after a while, you can keep opening it and it makes no difference. It's like it's saturated. A transistor's the same. You can't have a transistor more open, more conducting than just fully on, because that's its resistance is practically 0. So that's where it hits this point here, the saturation voltage, and after that point there's no linear relationship between IC and IP. So this bit here, the linear region, is where this holds. We can multiply the base current by HFE to find the collector current. Down here, the transistor doesn't get hot because it's like that now. Okay, there's no current flowing. There's a high voltage across the transistor, but there's no current. For power, okay, you multiply current times voltage, don't you? You need both. So here we've got a high voltage but 0 current. P is 0. So no heat is produced in the transistor. Here though, we've got a mixture of I's and V's. Here we've got a high V and a low I, but here they're half and half. And then down here we've got a low V and a high I. So either way, here we're going to have heat produced in the transistor. That's when they get toasty. When it's fully on, then we've got no voltage, but we've got a high current. Still no power. Okay? So therefore, hot in here, cold and cold. And that's where the MOSFET has some advantages in the fact that this linear region is shorter, but when it is fully on, it still has a little bit of resistance, so it gets a bit hot then. So the swings around those. But anyway, transistors generally better for lower currents and amplifying music and things like that. So how do we work out this? Well, we have to be able to sketch this graph. we have to sketch that graph. We need to establish easy enough the voltage level here, because that's the power supply voltage. This one never changes, so we know this point here at 0.7 never changes. So the only thing we need to establish, we know this point here, because that's where that meets with that. The only point we actually need to calculate to find out our voltage characteristic of the transistor is the point where it saturates. Okay, so if we can work that out from a circuit diagram, the saturation voltage, we can draw the rest. Right, how do we do that? We've covered that, but we've got the current gain formula, HF equals IC over IB. Let's do this example here. Okay. A light sensing circuit, I'll clear the writing off so we can start again with it. A light sensing circuit below contains a transistor with a current gain of 250. So 250 times more current will flow through the buzzer here when it is light. The resistance of the buzzer is 300 ohms. First of all, determine the value of V in that will cause the transistor to just saturate. So to do that, we need to really find out first what IC is, and then using HFE we can work out what IB is, using that current gain formula. Once we've done that, we know IB, we can use Ohm's law to work out the voltage across that resistor, and then we have to add on to that, what's the voltage across here always? What's the base of the transistor, the magic voltage? 0.7. So, what we need to do, calculate IC, gain formula to calculate IB, Ohm's law to work out the voltage across the resistor, and then add 0.7 volts. Okay, that's all there is to it.
Is it Ohm's law accounts to find IC?
Yes.
Yeah, it's 600.
This is just, yeah, so sometimes you have to work that out first. So we've got IC here equals 6 divided by 300. Okay, we know that. So what's 6 divided by 300? Is that 50 milliamps by any chance?
It's 20 million. Whatever.
Oh, right, yeah.
Yeah, 20 now.
20 milliamps.
So,
Oh, right, I'm not going to go for 20 milliamps. So we've only got a little incy current that runs a buzzer anyway. It's hardly like this thing with 3,400 milliamps. So we've got 20 milliamps going down here. So what do we have to divide that in to get IB? Divide that by...
HFE.
Yeah, so we do 20 times 10 to the minus 3 divided by 250. What does that give us? 8 microamps, 80 microamps.
Yeah, it's 80 million.
Yeah.
80 microamps. Yeah, 80 times 10 to the minus 6.
Yeah.
That's 80 microamps.
Actually.
Okay, now we've got the aim button on the calculator working.
Yeah, that's what I pressed, but I did it
We
wrong.
read it in milli rather than micro.
Yeah.
So be careful there. So we've got tiny current going into the base of 80 microamps. Okay? How do we work out the voltage across the resistor then?
So it's just times 10 to the 3.
Yes, good. So therefore the voltage, am I right here? Voltage across RB is equal to 80 microamps, that's 80 times 10 to the minus 6 multiplied by 10 times 10 to the 3, which gives 0.8 volts.
So do you have to add 0.7?
Yes, that gives you 0.8 volts. But the thing that everybody forgets to do is add 0.7 volts,
1.5.
which gives 1.5 volts. They're not that bad, are they? These get everyone every year hates these. But the problem is they do mess it around a little bit and give it you backwards and stuff. But that's basically how they work. Then you have to draw the voltage transfer characteristic on the grid provided. And there we have it. Okay? What we need to plot is that point. Power supply voltage 0.7, 1.5.
Easy.
Okay. We'll carry on. The resistance has, the LDR has a resistance. This is where it gets into Thevenin's and loading transistors. This is why I like MOSFETs, because you don't have any current flowing into the base. You just use voltage, so you don't have to worry about this. But we're going to show by calculation the transistor is saturated at 200 lux. So we know that that's 2.5K. If we go back to here, we're making that 2.5K. So we use the potential divider formula. 6 times 1 divided by 1 plus 2.5 is 1.7 volts. Okay? Is that low? Is that saturated?
Yeah.
Yeah, because it's saturated at 1.5. So that means it is saturated. I'm on the wrong page. Okay? Calculate the power dissipated in the transistor at 200 lux.
Do you use the RMP or ISP?
Yeah. You could use either, but the problem is, what is R and what is... It's fully saturated, so what's the resistance of the transistor?
Infinite.
No, fully
Zero.
on. Everything's allowed to flow. The other way. Zero.
So we
Okay.
just do from nothing.
Zero. Calculate, describe one disadvantage of this circuit. You could say the linear region would mean overheat in the linear region. It might not actually, not much current anyway. I suppose what you could say, it's not going to be an instant switch on you, because that's going to have like, it's supposed to be a light alarm. You should have said something, you know, like, you know, this is doing it, isn't it? It's not fully, you've got that linear region there, which it's alright for some stuff, but if you've got a slowly changing input like that, it's not what you want, is it? So that's where you put a Schmidt-Knott gauge. How can this disadvantage be overcome?
Heating.
A Schmidt-Knott gauge,
Oh,
Schmidt inverter,
that's what I
or a comparator circuit. Remember the op-amp comparator circuit? So that'd be Schmidt inverter.
Not a very simple
You've
one.
done that. Okay, so that's transistors, so I'll stop the video.